Okay, so starting unit 2, in dynamics, we're still going to look at the same kinds of motion that we looked at in the last unit, but instead of just looking at displacement, velocity, and things like that, we're going to be looking at now the forces that contribute to those types of movements. Okay, dynamics is all about forces, work, and energy. Okay, so we'll be talking a lot about pushing and pulling and different systems and things like that in this unit. For today, we are going to talk about the simplest part of forces, and that is Newton's first law. Okay, now let me ask you this question. You ever see a skinny sumo wrestler? I haven't. I think they lose a lot. Why? Why are all sumo wrestlers such big people? In case you're unfamiliar with sumo wrestling involves two people trying to push the other out of a ring. Okay? It's not like WWE or anything like that. It's two people pushing each other around. Okay? And one person gets pushed out of the ring, that's how you win. Okay? Why is it such an advantage to be a very big person in that sport?
Big people are harder to push.
Exactly. Big people are harder to move. Okay? It's also why you don't typically see skinny guys on the offensive or defensive line in football. Okay? Those are usually the biggest, strongest guys because they're the hardest to push around. Okay? They have more, starts with M. Mass. Yeah. Okay? Mass is everything when it comes to forces, acceleration, and things like that. Okay? Now, mass is important for Newton's first law. It's important for Newton's second law, third law, all of his laws. Okay? But it's especially important in first law. Okay? Newton's first law goes like this. If I leave that desk alone, it will stay right there. Well, duh. Okay, of course it's not going to go anywhere if I don't do anything to it. Okay, that's Newton's first law. It's part of rocket science. It's not rocket science in terms of its difficulty, okay, but it's certainly part of it. If I don't exert a force on something, and there's no other forces acting on it, or at least all those forces are balanced, it won't do anything because everything is offset. Okay, how many forces are acting on that desk right now? Well, if there was only one force, then it couldn't possibly be balanced, right? It's easy to identify the first force. What's the first force? Gravity. Gravity's pulling on the desk. But if only gravity was pulling on the desk, it would be accelerating at 9.81 meters per second squared. What's keeping it from doing that? What's it sitting on? The floor. Okay? So the reason, if you've been standing for a long time, the reason your feet get tired is because the floor is pushing on them. Okay? Gravity pulls you down to the floor, and the floor pushes back, and you don't go anywhere. You just sit there. Same as this desk. Okay? Right now, gravity's pulling the desk against the floor. The floor is pushing up with an equal and opposite force. That's incidentally Newton's third law. Okay? And as a result, there's no unbalanced forces acting on the desk. Okay? If I was suddenly to pull the desk, okay, now there's a third force, and it wasn't balanced. So what did the desk do? It accelerated. Okay? It made a move, okay, toward me, because that was the direction of the unbalanced force. Okay? Gravity and normal force, that's the force of the floor, okay, we're balanced. They're still balanced. Okay? I'm just pushing this thing horizontally. Okay? Now, if I do that again, okay, I'm pushing it horizontally. There's actually no unbalanced forces on it while I was doing that, because it wasn't accelerating. So gravity was pulling down, the floor was pushing up, I was pushing that way. What was resisting me? Listen for it. What force would cause that to happen?
Friction.
Friction, yeah. Okay? In that case, there were 4 forces acting on that desk, and they were all balanced. Okay? It moved at a constant velocity. It didn't accelerate. Okay? Constant velocities mean there's no unbalanced forces. Think about how many people have ever used the cruise control in their car. Okay? Cruise control works by making sure all the forces acting on your car are balanced. Okay? So it's got drag from going through air resistance, rolling friction against the road. Okay? Maybe you're going up a hill a little bit and there's some gravity involved. Okay? All the cruise control does is make sure that the forward force balances out all the backward forces, okay, and keeps you going forward at a constant speed. Okay? Your cruise control uses Newton's first law to make sure there's no unbalanced force. Okay? Does that make sense? Sometimes it has to apply more force. Like on Sunday, if you were driving, anywhere on Sunday, okay, it might have had to apply more force if you were traveling south because the wind was blowing 90 kilometers an hour on Sunday. Okay, your car would have worked a lot harder. Okay? So if you're traveling at a constant velocity, it also means there's no unbalanced forces. If there are unbalanced forces, the object will accelerate. Okay? Unbalanced or net forces cause accelerations. Balanced forces cause an object to either sit still or continue traveling at a constant velocity. Okay? Everybody all right with that idea? That's Newton's first law. Okay? Newton's first law simply says that in the absence of a net force, an object will continue to do whatever it was previously doing. It will either travel in a straight line at a constant velocity, or it will sit still, one or the other. Okay? Now, NASA is obviously very concerned with this law, because once you get something moving in space, what will it continue to do? It'll just keep going. There's nothing out there to slow it down. There's no friction. It's a vacuum. Okay? So once you get a spacecraft or any other object moving, it's going to continue to move along that path until acted upon by an external unbalanced force. Maybe it comes close to a planet. Well, then the planet's gravity will pull it in, okay? And it'll accelerate towards that planet and it'll turn. Okay? But if it doesn't go by any planets, okay, it's just going to keep right on going. Okay? Like many of our spacecraft that we've sent into the deep reaches of space. Okay? The 2 Voyager spacecraft, okay, they're just going to go, okay? Because they don't have any fuel to stop. They're just going to go. Okay? It's also why NASA uses the gravity slingshot method. Okay? You've heard of that, the gravity slingshot, right? They used it to save Mark Watney in The Martian. Okay? If you want to accelerate but not use a lot of fuel, you use gravity. Okay? You come in close to another planet, you let it speed you up, and then you shoot off in a different direction, and you're going faster. Okay? It uses it uses a little bit of fuel because you got to jet away, but it doesn't use the same amount of fuel as just trying to accelerate with engines to go that fast. Okay? So we use that to turn spacecraft, and make them go faster and save fuel. Okay? The downside is, if you run out of fuel, what are you going to do? If you don't have any fuel?
Keep moving.
Yep. You are going to do what all of our spacecraft are currently doing. Bye-bye. Okay? They're just going to keep going in a straight line at a constant velocity. Okay? Because they don't have any fuel to do anything about it. Okay? That's a big deal if you're an astronaut. Okay? It's why astronauts very rarely do an untethered EVA. Okay? An EVA means an extravehicular activity, so they go outside of the spacecraft in a suit. Okay? They very rarely do that without a tether. Because if they were to use up all their little maneuvering jet fuel, okay, they'd be screwed. There'd be nothing they could do to change whatever velocity they had at that point. Okay, and that would be dangerous because then retrieval would be very difficult. Okay, so astronauts are acutely aware of how much fuel they have. All right, so we got a few videos to watch. It's gonna be a video heavy day because there's lots of Newton's first law kinds of things here. So using Newton's first law, your seatbelts use Newton's first law, and your airbags use Newton's first law. you ever get in the car, you're in a hurry, you pull on the seatbelt and locks in place, and you're too much of a hurry to let it go back in, even though you know that's what it's got to do, okay? Well, the way that mechanism actually works is using a pendulum, okay? When you make it catch, it's just because you jerk the whole assembly and it latched. But what it does in a crash is the pendulum moves forward because it has to. The car stops, the pendulum keeps moving forward, and it tilts the locking bar into place so that the seatbelt can't unwind. Okay? That's what locks your seatbelt in place. Your airbags work on a sensor that is exactly like the one that tells your phone which way you're holding it. Okay? It's basically a wire switch with a metal ball inside. Okay? If you stop suddenly, the metal ball will go forward, touch the wires on that side, complete the circuit, and detonate the airbags. Okay? The more that ball moves around inside of there, the more airbags go off. Okay? So if you have a lateral acceleration, the side airbags will go off, okay? All of those kind of things. Okay? It works on an acceleration sensor. The first ones didn't. The first ones were a contact sensor. So you could go up and kick the front bumper of the car and set off the airbag. Okay? Because they were just a contact switch. Okay? That doesn't work so well. Right? We want one that goes off only when there's enough acceleration for it to be needed. Okay? It reduces repair costs. Okay? You don't need it to go off unnecessarily. Okay? So they both work on the same concept. If the car stops suddenly, that ball moves forward, completes the circuit, boom! Airbags explode, you live. Okay? All right. Test tomorrow. If you want, you can write into scheduled help. Okay? I will give you that period of scheduled help if you want a little bit of extra time. Okay? All right.